Welcome back to the Explainer, everyone. All right, so in Module 1, we marveled at the massive energy packed inside the atomic nucleus and how it just naturally, gradually leaks out through radioactive decay. But today, we're diving straight into Module 2, nuclear reactions. We're going to get right into the subatomic mechanics of how nuclear reactors actually generate those incredible amounts of power right on demand.
Which brings us to a massive engineering question. What if we don't want to wait for natural nuclear decay? I mean, how can we trigger that extraordinary stored energy exactly when and where we need it? Well, to do that, we really need to understand the interactions between tiny particles and massive target nuclei. Basically, we need a trigger. And here is our trigger, the neutron. It's basically nature's perfect nuclear bullet. Why? Well, because it's electrically neutral. Think about it. If you try to fire a positively charged proton or an alpha particle at a nucleus, it just slams into the Coulomb barrier. That's the repulsive electromagnetic force from all the protons packed inside. It takes a massive amount of kinetic energy to punch through that force field. But our protagonist, the neutron, it completely lacks an electrical charge. It just slips right past that barrier and can wander straight into a nucleus, even at extremely low speeds.
Section 1, the probability of impact, navigating the atomic obstacle course. So, navigating this microscopic space is really the central problem of reactor physics. We've got our neutron bullet, but how do we mathematically figure out the probability of it actually hitting a target as it travels through a material? Well, that probability is measured by something called a cross-section, represented by the Greek letter sigma. So the crucial point here is that a cross-section isn't literally a physical geometric area of a target. Not at all. It's a quantum mechanical probability of interaction. A large cross-section means our neutron is very likely to interact with a specific nucleus. A small one? It'll probably just pass right on through. And as we'll see, this probability changes dramatically depending on how fast the neutron is moving.
Okay, real quick, I just have to share this brilliantly weird unit of measurement physicists use for cross-sections, the barn. It equals 10 to the negative 28th square meters. So where on earth did that come from? Well, during the Manhattan Project, American physicists were measuring the surprisingly large interaction probability of uranium, and they joked that hitting it was quite literally like hitting the broadside of a barn. And, well, the name stuck. So what actually happens when our neutron strikes a nucleus? There are a few possible non-fission outcomes here. First, we have elastic scattering, where the neutron just bounces off the nucleus like a billiard ball, transferring some of its kinetic energy. This is absolutely essential for slowing neutrons down, especially when we use moderators like hydrogen. Then there's inelastic scattering. Here, it bounces off but leaves the target nucleus excited, causing it to release a gamma ray. And finally, radiative capture. The neutron is completely absorbed, a gamma ray is emitted, and the neutron is permanently removed from our chain reaction. And yeah, that last one is a really big deal.
Section 2, navigating the danger zone, the threat of resonance absorption. Now, this is a highly perilous part of our neutron's journey. As these fast-moving neutrons bounce around and start slowing down, they pass through a very specific energy range between 1 electron volt and 10,000 electron volts. In this resonance region, the probability of absorption by uranium-238 spikes wildly. We're talking by several orders of magnitude. If a neutron gets captured here, it's swallowed up. It doesn't cause fission. Instead, it turns into uranium-239, which eventually decays into plutonium-239. Now, while that does breed useful plutonium, it means our neutron is totally lost from the power-generating chain reaction. Because of this, reactor designers have to work incredibly hard with fuel and moderator geometry to get neutrons safely past this danger zone intact.
Okay, let's dive right into the climax of our neutron's journey. Section 3. Fission and chain reactions, the main event. To really visualize the mechanics of this, imagine the heavy nucleus as this wobbly liquid drop. Step 1, the heavy nucleus absorbs our neutron. Step 2, this newly formed compound liquid drop becomes so energetically strained it just starts oscillating violently. Step 3, the drop elongates and narrows right at the middle. And finally, step 4, it pinches off entirely into 2 distinct fission fragments. The incredible strain literally snaps it into pieces. And in the process, it releases massive energy, plus an average of 2.4 brand new fast-moving neutrons to keep the whole cycle going. Now, we really need to clear up a vital distinction in terminology here between fissile and fissionable materials. Fissile materials, like uranium-235, readily fission when struck by neutrons of almost any energy, but especially those incredibly slow thermal neutrons. In fact, U-235's thermal fission cross-section is a massive 580 barns. On the flip side, fissionable materials like uranium-238 require highly energetic fast neutrons. We're talking over 1 million electron volts to fission. They completely ignore slow neutrons. For U-238, that fast cross-section is just 1 barn. That is nearly a 600-fold difference. This perfectly proves exactly why slow neutrons are so much better for driving our reactors.
So, the crucial point here is the sheer scale of the energy released. One single fission event releases about 200 million electron volts, or MeV. But where exactly does it all go? Well, the lion's share, roughly 168 MeV, goes purely into the kinetic energy of those 2 fission fragments we just saw pinch off. They violently slam into the surrounding material, and that kinetic energy converts into the intense heat that ultimately drives our power plant turbines. The rest of the energy just sort of trickles into prompt gamma rays, prompt neutrons, and delayed decay energy. To sustain this microscopic heat generation over billions of these atomic hero journeys, we have to look to the macroscopic scale with the multiplication factor, or K. This is simply the ratio of neutrons in one generation compared to the previous one. If K exactly equals 1, the reactor is critical, meaning power is perfectly stable and self-sustaining. And here is a huge takeaway. The laws of physics literally dictate that a commercial power reactor cannot explode like a nuclear weapon. Power reactors rely entirely on slowing neutrons down to cleanly keep K precisely at 1. Nuclear weapons, however, require entirely fast neutrons to create a rapidly uncontrolled supercritical state in mere microseconds. Section 4. The Art of Moderation. Taming the fast neutrons. So how do we actually keep K equal to exactly 1? Well, by intentionally taming those chaotic, newly born fast neutrons. Let's look at the life cycle of our neutron, a vital cooling process called thermalization. Point 1. The neutron is born from a fission event, moving blazingly fast at up to 10 million electron volts. Point 2. It begins bouncing off surrounding atoms, losing energy and slowing down into epithermal neutrons, where it has to run the gauntlet of that dangerous resonance region we talked about earlier. And point 3. It finally becomes a fully thermal neutron, having dropped to a massive energy low of a mere 0.025 electron volts. It's now traveling at a leisurely 2,200 meters per second, fully in equilibrium with the surrounding atoms, and perfectly primed to successfully trigger fission in U-235.
So, how do we physically slow them down? We use real-world moderator materials. Now, an ideal moderator needs low atomic mass, high scattering ability, and crucially, very low absorption, so it doesn't just swallow our hero neutron. Light water is cheap and great at slowing neutrons, but it does absorb a fair amount, so we have to use enriched uranium to compensate. Heavy water, where the hydrogen is replaced by deuterium, has 700 times lower absorption. This allows us to use cheap, natural, unenriched uranium fuel. But producing heavy water is incredibly expensive. Then there's graphite. It's a solid, which opens up different geometries and has low absorption, but it's flammable at high temperatures, which, as you might know, was a major contributing factor to the severity of the Chernobyl accident.
Section 5. Fission versus fusion. The complete nuclear landscape. To truly grasp the mechanics here, we need to complete the picture by contrasting our fission journey with fusion. Fission is splitting heavy nuclei down the binding energy curve, releasing about 200 MeV per event, but it leaves behind long-lived radioactive waste. Fusion, on the other hand, is joining incredibly light nuclei, like deuterium and tritium, up the binding curve. That releases 17.6 MeV per event, has virtually limitless fuel, and very low waste. But here's the massive hurdle. To overcome that positively charged Coulomb barrier and literally force 2 light nuclei together, fusion requires 100 million degree plasma. So while fusion holds incredible long-term promise for the 2040s and beyond, the extreme heat required to achieve it keeps fission firmly as our current practical domain for power generation. All right, so we have our thermalized neutrons sustaining a perfectly critical chain reaction. But I want to leave you with a provocative thought here. When U-235 fissions, the vast majority of those newly born neutrons appear instantly. But what if a tiny fraction, just 0.65%, didn't arrive immediately? What if they were delayed by seconds, or even minutes, as fragments decayed? Think about it. Without this incredibly tiny fraction of delayed neutrons, physically controlling a nuclear chain reaction with mechanical control systems would be completely impossible. The reaction would just happen way too fast.
So how do these delayed stragglers single-handedly save the entire concept of nuclear power? Well, that is exactly what we're going to uncover in our next module. Keep learning, and I'll see you then.